my search window, and I'm going to type in GitHub MetaMorpheus. And so all of our software, MetaMorpheus is just one of the programs that we write, is available on GitHub. It's totally open source. We use a very liberal MIT license, so people can kind of use it however they want. They can repackage it, repurpose it. We want anybody that wants to take advantage of the work that we do to have access to it. And so everything's here on the GitHub. You have to scroll down a little bit, okay, to finally sort of get to the text here. There's a couple things that I sort of like want to point out. Right here where it says download the current version here, we're going to click that just in 1 second, and then that's going to sort of download it to my machine. But before I get there, I just want to talk about some system requirements, okay, so it'll run. All right. This is the kind of key one. If you're running in a Windows or Mac or Linux environment, you need to have compatibility with .NET Core 3.1. Okay, so it will work in all those environments. There's no GUI for Mac, but you can run it from the command line in Linux, provided that you have the .NET Core 3.1 installed. I have a bit of a bigger machine, but we recommend at least 8 GB of RAM, and it's naturally multi-threaded. So the more cores you have, the faster it's going to run. All right, so here we go. And so by clicking that button, it's going to automatically take you to the most recent release. Once you have it installed, every time there's a new release, it will notify you when you open MetaMorpheus up. Okay. And for Windows applications, we're going to download the installer here at the top. But if you want it to run in the Linux command line, you would download this command line.zip and just operate it from there. Rob's going to talk about that a little bit later, how to run the command line and so forth. I'm just going to sort of stick with the GUI for now. So, so here we are. We're going to save the file, and I am opening up my downloads, and you can see here's the installer right here at the top, and I'm just going to double click that. And while I'm waiting, I'm just going to, oh, it says don't run, but really you should. You have to click on more info and run anyway. Next, install. All right, and we're just going to launch MetaMorpheus. And there you go. So MetaMorpheus is now totally installed. Now I'm going to see if I can just share part of my screen so that gets a little bit bigger and it's a little easier for you to see.
Now you had said that every time that you kind of do this in front of an audience, it's somewhat surprising. I'm
completely shocked every time that works without like that, you know what I mean? I don't know, I shouldn't be at this point because it's been around a long time, but I had the same experience your friend has, and I have had forever, which is that nothing anyone else ever wrote ever works really fast. And I from early days, I wanted this to be so easy, even I say this, so easy even a PI could do it. And so so that's kind of been our goal in terms of making it sort of user friendly. Okay. Before I'm gonna show you one more thing on the GitHub before we launch into this. Okay. Let's show back here. All right, so we're going to go back to the main MetaMorpheus page, and this is really handy for new users. Okay, right down here we have an explanation of how to do some test data and how to do how to test your installation is working. Okay, so if you open up this box folder here, what you're going to see is there's a couple folders. One folder's got some MZML files that have already been converted from .raw. One folder's got FASTA database files. And then there's like a number of like search tasks here, okay? In addition to that, we have the 2 original raw files. These are from mouse data that we published a while ago. And I think after we save this video, we can provide links to that down in the description. And then there's a couple additional style databases. Rachel, in just a minute, is going to explain about how to use tasks and so forth. But I just wanted to show all of this stuff is here. And I already have it downloaded on my machine. And so that's what I'm going to use to start this video out. But I just wanted to explain how we got the data that we're using for this test. Okay. All right. So this is the MetaMorpheus vignette file. You'll recognize that those are the same files that we had before. Okay. So here's the GUI, and the GUI is arranged kind of how you use it in order. All right. And so the first thing you're going to do is add in the databases. Then the next thing would be to add spectra. The third thing would be tasks. In this case, the task is going to be a search task. And then the last little thing is run. All right. Like as I said, Rachel's kind of go through this in greater detail in just a second, but I'll show you how this works. So if you click on databases, you can see that there's an empty area where files go. And I can just simply drag one of the FASTA files from here down here, and it will just drop in. Okay. We have already curated a list of contaminants. And if you want to add default contaminants, you can just click that button. Okay. So now you've got a contaminants file. If you decide later you don't want to use that, you can uncheck the box, or you can just hit the delete button and it'll go away. But we'll just throw it on there for now. Okay.
Can you just, if I imagine someone, what's in your contaminants file? Is this like about 100 things?
Exactly.
Or...
Like a whole variety of things. Originally, we started with the CRAP database. That was the beginning. And we've adjusted it a little bit since then. Dr. Brian Fry in our lab poured over it quite a bit. And it also, we've added PTMs to those things. And so Rachel will talk about using XMLs, but most CRAP contaminant databases just have the base protein amino acid sequence. Ours also includes PTMs from those organisms. And when you get the results, it'll show you whether it's a target protein or a contaminant protein. Okay, so you have the option to filter, because you can imagine there's like human keratin in here. That's a common contaminant. But if you're using a human database, okay, by default, it won't use the contaminant human, right? It'll sort of exclude things from the same organism. You get the choice to exclude those from the same organism. Okay.
So an example of like a PTM on a contaminant is like methylated trypsin, because like trypsin manufacturers methylate their trypsin so it won't auto digest. So like our contaminants database will help you look for those things if you want.
Wow. No, that's
also has like some of the components of like cell culture media that can get carried along. So bovine serum albumin, etc., to look for in case you don't fully wash everything off of your cells before lysis.
Yeah, that's I mean, I love to hear about the complexity of that, because for those people, when we say CRAP, that's the common repository of advantageous proteins, right? And that was kind of an old one from, I guess, Ron Beavis, right?
Yeah.
And that had things like, even had like latex and wool, but you're like kind of taking it up a notch, which is things I didn't know. So that's really cool.
I mean, I think people like to use it, but nobody ever really knows what's in there. And I think some people kind of use it sort of blindly. To be honest, ours started with the CRAP. We also borrowed heavily MaxQuant, Andromeda search engine. They provide a contaminants database. We also like looked at theirs, and so we, combined some of that. So, like full disclosure, standing on the shoulders of giants here. This isn't like a product of our own work. It's it's incremental improvement on some excellent scholarship from other people before us.
Right.
Next thing is spectra. You see the same basic panel, okay? So I'll go back up here to the vignette and I'm gonna just grab raw. This is a thermo raw file format. You can also use .mzml, okay? I'm gonna drag this in here and you're gonna see at some point soon when I try to run this, it's gonna prompt us to like agree to a thermo license, okay? But it will read thermo raw file data natively. So you don't have to do any file conversion if you don't want to, like you can just sort of save the time.
So not to interrupt, so it's MZML, MGF, or RAWs.
That's correct.
Okay, so but like with other tools or read or writers, you know, you could make those, right?
That's right. If we have a second at the end, I think Rob is going to just pop MS convert up quickly and show you the parameters that we use to convert from like raw to the MZML style that we like. I do want to point out that we do not favor MGF. And this may be getting into the weeds a little bit, but we like to deconvolute the spectra and pull out additional IDs, and oftentimes MGF kind of throws away MS1 spectra and it just gives you whatever precursor mass. And so that's like a much diminished data set. We would really much rather have MZML or .raw because we can pull a lot more IDs out of it. But you can read MGF. All right, and so we're on to the tasks here. And you see there's a number of tasks: calibration, PTM discovery, search, crosslink search, and glyco search. Right now, I'm only going to talk about search, okay? So you add the search task, and what it's going to pop open is it's going to pop open the parameter tables here, okay? And we hid a lot of stuff down here in advanced options. And so I'm not going to talk about any of this stuff because I want people to sort of see. I'm just going to add the task. And that's all you need to do. Like, you don't really have to play around with it like too much unless you have some sort of, you know, more unusual data set. Okay. But Rachel's going to kind of go through those parameters when she talks about, like, you know, the next round of search. All right. So here we are finally at the run task. We have databases up here, raw files on the left, and then all of the tasks. You can add as many as you want. They'll just run in order and pipe right into each other. Here we have just the one. And this is showing you where the data file is going to be. So I'm going to hit run, and you're going to sort of see real-time search. Ben, you see down here, this is the case where it's showing you there was conflict between the mouse database that we used to search and the contaminant database. And it's telling you sort of explicitly like which accession numbers are not being included as a consequence.
Okay. So you can, I mean, there's kind of different, I think, schools of thoughts on like a vignette, right? But I mean, basically you're saying, you know, with these files, you can pretty much go through, use defaults, and you're going to go through, you're going to have results at the end. We're not going to be throwing errors. We're not going to be hitting these kind of more advanced problems.
That's right. And we provide, or we used to anyway, we used to provide the results of all of this. And so what you could do is you could pop open a couple of like Excel tabs and sort of look side by side, and you should get this same exact answer like every single time. Okay.
Yeah, if you're running a like an Orbitrap, you know, high resolution MS2 bottom up trypsin sample, you really don't need to mess with any settings at all. That's the defaults are sort of built for that sort of scenario.
And for, I mean, I imagine like someone who has no idea what we're saying, like what your words just said, like if you go and download data from Pride, those words should be there, right? Like it's a trypsin, it's going to say probably Orbitrap or high res, like that'll be in there somewhere. And yeah, so those settings are totally fine for MS. So a fragment ion high res type experiment.
Yeah, that's right. And we're going to talk about cases where you need to make those adjustments when Rachel gets around to her section. So our search is totally done. Okay. You can double click on any one of these like files and it'll open that file directly, or you can hit the open button, and what open's going to do is just going to pop open the results folder. By default, you can see that it appeared up here in the same folder where the raw files were. So that's the default. Wherever you draw the raw files in, that's where the results are going to end up. Okay. And it's named with the date and time. Okay. And so you can search the same thing sort of like over and over and over again if you like, and it's not going to overwrite it. It's just going to like plop it down here as like a new time. Okay. In this folder, there's a couple things. We have a task settings folder that's going to include like all of the settings that were used. So if you want to run the same search over again, or you wonder what the parameters were from your search, you can open this folder up and have a look at those files. Rob's going to talk about that kind of at the end. And then there's a search task folder. Okay. And in the search task folder, there's several files. We have the PSMs, the peptide spectrum matches. We have a peptides file, which contains the highest scoring example of every different PSM. Okay. There's an output. Some people like to run percolator on the PSMs after the analysis, and so we formatted a file so that you could read it directly. You wouldn't have to reformat our results if that's the kind of thing that you want to do. And also by default, quantification was turned on. Okay. And so what we have here are two files for quant. One would be the peaks quantified, and one is the peptides quantified. Okay. So peaks meaning like PSMs, and this would be like across files, and then peptides again was the example. And then there's one file that contains both the inferred proteins as well as the protein quant. Okay. Rachel's going to go through like all of the she's going to pop these files open and kind of like walk you through the steps, but I wanted to just show two additional files here. The first file is just it is a simple text file with the results. Okay. In this one raw file, the total search time was 1 minute and 6 seconds. There was 14,000 PSMs, 5,700 peptides, and 2,500 proteins. There's only the one file, so it tells you like how many spectra were analyzed and so forth. Because there was an XML for the contaminants database, there's some like listing of a few PTMs that we saw, but you'll see how that expands greatly when we do the PTM discovery in a minute. And that's basically it for like sort of a high level.
Hey, Michael,
Yeah.
hold on. So you had a raw file. Did we use the raw file here? So we've loaded a raw file, 25,000 MS2s, 1 minute. Like, what is your computer? Just give me like a perspective here. Like, do you
let
have
me show
like
you what the computer is here.
Okay.
All right. So I'm gonna.
That seems really fast to me, and I know it is fast, right?
Yeah.
But like,
let me open up the pros file here. Okay. So the pros file is made so you can kind of drag and drop it kind of into a paper. It has like just a condensed version of the parameters, like your sort of search parameters and stuff, but it plops in there your computer. Okay. And so this is a fast, powerful computer. It's got 28 threads and 128 gigabytes of RAM. Okay. On Rachel's like laptop, it's a good bit slower. Okay. You can sort of like run it in human time. You can certainly search files faster than you can take them. But it's not like, crazy fast, if that makes sense. It's like, it's human fast. It's not, our good friends in Michigan with MS Fragger, like they're sort of like at the next level with speed. But this is perfectly reasonable sort of response time.
I just had to say that because, I mean, not that like you said, I don't think it's unreasonable, but like that was really fast. I just had to ask, like, what are we doing here?
Search is
Yeah.
also the fastest task. Calibration of GPT and B take a little bit more time.
Got it.
For my
Yeah,
laptop, this would take about like 5 minutes. With
That's still
the-
really
the
fast.
spot. So yeah,
Yeah, it's no slouch. I mean, let's just say that it's no slouch. But okay, cool. No, those files Rachel's going to talk about. Yeah, I'm excited about that.